So let us see now what are the factors influencing splitting of d orbitals. Factors influencing splitting of d orbitals. Factors influencing splitting of d orbitals. First one. Look here, same metal ions with the different charges. Same metal ions with the different charges. One I am writing FeH2O taken 6 plus 2 complex. Another one also same iron complex FeH2O taken 6 plus 3. Same metal ions, look here, but different charges. Greater the charge density, greater will the splitting. Lower the charge density, lower will the splitting. Now, this is having definitely less delta O. Less delta O, this will be having high delta O. Splitting of d orbitals is less, splitting of d orbitals is more. Same metal ions with different charges, greater the charge density, greater will be the splitting of d orbital. Coming to second point, different metal ions with the different charges. See, iridium complex I am writing, iridium aqua complex. Second one I am writing CrH2O taken 6. Then different metal ions with the different charges. This I am writing with the plus 2 charge. This I am writing with the plus 3 charge. See, different metal ions with the different charges, provided electronic configuration is same. Both are having D3 configuration. Yes, vanadium plus 2 is D3, chromium plus 3 is D3. Different metal ions with the different charges, provided electronic configuration is same. Once electronic configuration is same, then you have to see the charge difference. Wherever the greater charge density, right, there will be the greater splitting here also. Once electronic configuration is same, check it, which is having greater charge density. Greater the charge density, greater will the splitting. Here also we can write less delta O, high greater delta O, less delta O and high delta O. From these two factors what we can understand, greater the charge density, greater the splitting. Therefore, charge density is directly proportional to splitting of d orbitals. Charge density means we can consider simply charge electronic, this electronic charge density, or you can consider here this charge density means positive charge over the metal ion. Positive charge of the metal ion, or you can consider oxidation number. So, charge density, positive charge of the metal ion, charge density directly proportional to splitting. Greater the charge density, greater the splitting. Greater the charge density, greater the splitting, charge density directly proportional to splitting. Next, third point, let me see. Now, different metal ions with same charge. Different metal ions with same charge, look the board. CO, H2O taken 6 plus 2, cobalt plus 2 complex. Now I am writing one more, nickel aqua complex, charge density again same, but electronic configuration is different. Electronic configuration is different. See here, different metal ions, yes, same charge. When charge is same, we cannot decide in which it is splitting of d orbitals is more. Then you have to check it, what difference, the difference is there in the electronic configuration. Once charge density, the oxidation number is same, see the electronic configurations of the metal ions. Now, one is D7 or one is D8. Now, lesser the number of electrons in d orbital, lesser the number of electrons in d orbitals, that will be having greater splitting. So, here high delta O you can consider for cobalt plus 2, and here is having what less delta O and high delta O and less delta O. How to explain this particular? In what way this particular configuration influencing the splitting? Now, lesser the number of electrons, consider this particular a ligand, a negative ligand is there, lesser the number of electrons. Suppose you are considering here D7 electronic configuration, say cobalt plus 2, consider nickel plus 2, D8, 2 are there. A cyanide ligand is actually forming a bond with this particular cobalt plus 2. Similarly, a cyanide ligand is forming a bond with nickel plus 2. This particular cyanide ligand experiences a repulsion from 7 units of negative charge, 7 units of negative charge. But in the case of nickel plus 2, it is experiencing 8 units of negative charge, repulsion from 8 units of negative charge. Then this particular cyanide is experiencing a little less, therefore the cyanide can easily penetrate very near to the metal ion. This cyanide can penetrate very near to the nucleus of the metal ion. So cyanide is approaching very near to the cobalt plus 2. But this particular cyanide cannot approach very near to the nickel plus 2. So it is penetrating more toward the metal ion, it is penetrating less toward the metal ion. Once a ligand is actually penetrating very near to the metal ion, then it is causing greater splitting. Therefore, cobalt plus 2 D7 high delta O and nickel plus 2 D8 less delta O. What we can make a relation between number of electrons in d orbitals and splitting? Number of electrons in d orbitals, number of electrons in d orbitals inversely proportional to splitting, inversely proportional to splitting. Greater the number of electrons in d orbitals, less splitting. Less the number of electrons, you can say that more splitting. So this is the relationship between number of electrons in d orbitals and splitting of d orbitals. So 3 factors. Next, coming to the 4th one. Consider quantum number. Quantum number. What is this quantum number? As the quantum number is increasing, consider 3D and 4D, you consider 5D. 3D, 4D and 5D. Let me write a 3D complex, CO H2O taken 6 plus 2. CO H2O taken 6 plus 2. Around the cobalt complex, what 3D. Let me write below this cobalt, rhodium complex to take H2O taken 6 plus 2. Rhodium complex plus 2. Then you take the iridium complex, iridium H2O taken 6 and plus 2 you take, plus 2. See, all are actually plus 2 oxidation state. All the 3 are having same electronic configuration. Then but one is 3D, one is 4D, one is 5D. What do you understand by this? Quantum number, principal quantum number is increasing. Number of orbits are increasing. As the principal quantum number is increasing, then delta O values all gradually increase. Delta O values gradually increase. Delta O values gradually increase. Once principal quantum number is increasing, 3D to 4D, 4D to 5D, delta O values also gradually increase. So cobalt complex is having less splitting and iridium complex is having high splitting. This is what influence of quantum number. Now coming to next one, let me take here next factor. First one, second, third, fourth and fifth. Fourth is quantum number, fifth one is field strength. Fifth one is field strength. Field strength. Field strength. You might be knowing one concept. Whenever a weak field ligand is causing less splitting, a strong field ligand is causing greater splitting of d orbitals. Simply we can say strong field ligand is causing greater splitting of d orbitals than weak field ligand. Simply field strength you can say directly proportional to splitting. A weak field ligand is there, suppose this is a strong field splitting, very high, and a weak field splitting is what? Less. Lesser splitting, more splitting, field strength is directly proportional to splitting. Next, one more factor is there, the last one, geometry. One more factor is there, the last one, geometry. Let me take a geometry we already discussed. three geometries, splitting of d orbitals in three geometries, tetrahedral, octahedral and square planar. The relationships also are given to you. Same thing we write here. See, fifth factor and next coming to sixth factor, geometry. Geometry. What we discussed? I clearly discussed all these. Delta SP is more than delta O, I said. Delta O is more than delta T. This is what order of splitting of d orbitals in three different geometries. These are the factors which are influencing splitting of d orbitals. Next. Now we will discuss next this spectrochemical series. And what is spectrochemical series? How the ligands are arranged according to increasing order of field strengths of the ligands. Next concept, spectrochemical series. Now, spectrochemical series. Spectrochemical series. What is spectrochemical series? The series which gives increasing order of field strengths of the ligands. The series which gives the increasing order of field strengths of the ligands known as what spectrochemical series. Based on this particular series, you can explain or you can understand which is actually a strong field ligand and which is weak field ligand. Means according to this particular spectrochemical series, we can classify the ligands into strong field and weak field ligands. Really, I write on the board 15 ligands. I put in the order of increasing order of their field strengths. Increasing order of their field strength. You have to remember all the ligands whatever I am writing on the board, because in the examination, in some of the entrance examination, they are giving order of this particular increasing order of field strengths of the ligands. If you are giving only few, they may give beyond that particular ligands. Therefore, entire series whatever I am giving on the board, nearly 15 I will give, entire series you try to remember, because in the examination they give only 4 ligands. They will ask you which of the following is the correct order of field strengths. Therefore, once you remember entire series, then those 4 ligands you can pick up and you can easily say what is the correct answer in the given multiple choice questions. Now, see, I am writing the order I minus E less than Br minus, less than sulfide ion S minus 2, then less than Cl minus, less than nitrate ion, less than F minus, less than this OH minus, less than C2O4 minus 2, and it is less than C2O4 minus 2, less than H2O, then it is less than EDTA, less than EDTA minus 4. It is less than NH3, NH3 and PY are having more or less same, EDTA less than NH3 PY, and it is less than En, less than BiPi. This particular again less than, BiPi is less than Ofen, orthophenanthrolene, Ofen, less than NO2 minus, less than you take PPH3, less than you can take Cn minus, less than CO. This is what order of the different ligands and their field strengths. According to this particular spectrochemical series, what I said, we can classify the ligands into weak field ligands and strong field ligands. Now, this particular ligands, all of these you can consider the what this particular H2O up to H2O you take, these are all what weak field ligands. These are all weak field ligands. Remaining EDTA you consider, EDTA, and remaining all these particular ligands, all you can consider what strong field ligand. These are weak field ligands, weak field ligands. These are all strong field ligands. Up to H2O weak field, the remaining all the ligands you can consider what strong field. You have to remember the ligand which is actually weak field, which is actually strong field. What is the importance of this particular weak field and strong field ligands? Wherever weak field ligand is there, that particular ligand is not pushing the electrons to pair up. Once weak field ligand is there, the electrons are remaining as such unpaired. The resulting complex is what? Paramagnetic. Once you take a strong field ligand, that particular ligand is pushing the electrons to pair up, electrons are getting paired. Resulting complex is what? Diamagnetic. So, what we can conclude now? In presence of weak field ligand, resulting complex is what? Paramagnetic. In presence of strong field ligand, the resulting complex is what? Diamagnetic. That we can understand. Therefore, it is better to remember entire series. What I said in the examination. In the examination, they are not giving entire series. They will give only 4 or 5 ligands and they will put a question to you. Which of the following is the correct order of field strength of the ligand? Therefore, you have to remember entire series, whatever I written on the board. Then we see distribution of electrons in T2G and EG orbitals. Next heading. Look here, distribution of electrons. Distribution of electrons in T2G and EG orbitals. Distribution of electrons in T2G and EG orbitals. First, let us consider octahedral geometry. Octahedral geometry. We have to make a table for this to understand the distribution of electrons in T2G and EG. Let me make a small table. Dn configuration. Dn configuration and consider first a weak field. Let me say it is T2G, EG orbitals, T2G and EG orbitals. Next, N I am writing here, N stands for number of unpaired electrons. Then consider it is what? Strong field next, strong field. In strong field also, here I am writing T2G and EG, T2G and EG. Then again you take N. Again N. So this table is important. How the electrons are distributing in T2 and EG for a particular complex. Now, to show this, I am writing just one splitting I will show. You know well, already we have discussed the splitting of d orbitals. Now we consider this is what D1 configuration is taught. This is higher energy level. This is lower energy level. This is T2G and EG. Now you consider first one D1 configuration. Yes, I written D1 configuration. After the splitting, the electron enters into lower energy level. Therefore, it is what? This one. So, we can write this particular configuration as T2G1, EG0. You are looking number of unpaired is only 1. Strong field or weak field, it makes no difference. Then T2G1, EG0, S1. D1 configuration, this is the distribution of electrons. Come to the next point, D2 you take. See, 2 electrons I am writing. After splitting, the 2 electrons entering into T2G. Then we can write it as what? T2G2, EG0, number of unpaired 2. Then it is strong field or weak field up to third electron. Up to third electron. We should not pair up the electrons. Say why? This particular T2G orbitals are actually degenerate. All are having equal energies. According to Hund's rule, what we say, all the orbitals of the subshell is whenever they are half filled, the next entering electron is actually getting paid. Therefore, in the case of T2G also, the 3 orbitals are degenerate. After the half filled only, the next 4th electron can pair up. Therefore, up to 3rd electron, even in strong field or weak field, the electrons are remaining unpaired. So, here strong field also should not pair up the electrons in T2G 2 and EG0, then it is coming to what? 2 unpaired. Coming to D3 electronic configuration, yes, D3. then it is T to the 3 is the 0. What I said, up to third electron, we should not pair with the electron. It is now half filled. Strong field also same, number of unpaired 3, and you can take T to the 3 Eg will be 0, number of unpaired 3. Next you take 4, D4 are written. See now, 1, 2, 3, fourth electron entering into higher energy level in the case of weak field. Weak field means what? The splitting is less. Therefore, electrons can, the way they are filling the lower energy level, they are also filling the higher energy level, as there is no much difference between the lower to higher. Therefore, here D4 configuration I am writing, yes, in weak field it will be T to the 3 Eg will be 1, number of unpaired 4. Now, talk about the strong field. What I said, wherever strong field there, splitting is more. When splitting is more, the electrons are not easily entering into higher energy level, the electrons are getting paired in the lower energy level only. Therefore, the 4 electrons are getting paired in the lower energy level. Now, it is T to the 4 is 0, number of unpaired 2, number of unpaired 2. The strong field what we can write is this electron entering into T to the number of unpaired is what? 2. Now, we consider next one, right, D5 you take. Now, D5 electronic configuration. Now, it is what? 1, 2, 3 weak field. This will be what? T to the 3 Eg 2. T to the 3 Eg 2. This is what? Weak field. So, D5. D5 it is T to the 3 Eg 2, number of unpaired 5. Okay. Strong field again. What do you know? Strong field splitting is more. The electrons are not entering higher level, getting paired in the lower level. So, first electron, second electron, third electron, fourth and fifth are actually entering into lower end level in the case of strong field. Therefore, T to the 5 Eg 0, number of unpaired you can take 1, number of unpaired 1. Next you consider D6. D6, I am writing here 6 configuration D6. Now, talk about this weak field. Weak field you take now 1, 2, 3, yes, fourth electron, fifth electron, then sixth electron is joining in the lower level. Then it will be T to the 4 Eg 2, number of unpaired you can take as what? 4. So, in the D6 configuration, this is the distribution of electrons, unpaired electrons we are looking on the board 4. Strong field. Now, strong field, now 1, 2, 3, fourth electron is getting paired here, fifth electron is getting paired here, next sixth electron is also getting paired here. Then this is what distribution of electrons. This is the distribution of electrons. Then you can take, now it is T to the 6 is 0, number of unpaired 0, number of unpaired 0. This is what strong field distribution. Come to the next one, 7 electrons. 7. Now, D7 weak field and strong field, let us take weak field. 1, 2, 3, fourth electron, fifth electron, fourth electron, fifth electron. Now, sixth electron is getting paired, seventh electron is getting paired. This is what distribution of electrons in weak field. Now, it is what? T to the 5 Eg 2, number of unpaired 2. Number of unpaired 2, yes, it is not 2, it is 3. Number of unpaired is what? 3. Number of unpaired electrons are 3 in what? D7 electronic configuration. Next, strong field. Strong field, all the electrons are getting paired in the lower energy level. 1, 2, 3, fourth electron is pairing, fifth electron is pairing, sixth electron is also pairing, the remaining unpaired electron is only 1. So, this is T to G, T to the 6 Eg 1, number of unpaired 1. Let me show next, this is what D8 electronic configuration, let me write 8 electrons, check it now. Weak field 1, 2, 3, 4, 5, 6, 7, 8, 8 electrons. Then it will be becoming what? T to the 6 Eg 2, T to the 6 and Eg 2, number of unpaired 2. T to the 6 Eg 2, number of unpaired 2. Next, strong field you take. Yes, strong field and weak field distribution is same. Look at here, 1, 2, 3, 4, 5, 6, 7, 8. Distribution of electrons in D8 electronic configuration in octal geometry, either it may be strong field or weak field. Distribution of electrons in T2 then is what? Same. In octal geometry, D8 electronic configuration, even in a strong field or weak field, distribution of electrons is same in this particular D8 electronic configuration. T2 is 6, EZ2, number of on page 2. This is the distribution of electrons in octal geometry in T2 then EZ orbital. How the question appear on this particular concept? I'll write a question, I'll explain that how the question appear, how to answer this. Now I am writing a question to see which of the following is correct distribution of electrons in T2G and EZ orbitals. For the complex, which of the following is the correct distribution of electrons in T2s and EZ orbitals? For the complex, look here what I am writing on the board. Nickel, you take NS3 taken 6 times plus 2. Then first option you take, it is T2G5 EZ3. Second option you take T2G4 EZ4. Next one T2G6 EZ2 D. T2G7 let me write EZ1. Now first you see what is the complex is given, nickel hexamine plus 2. Already given in the how to know the unpaired electrons and all, already given the concept about how to know the unpaired electron. Yes, nickel is what, 28, this is D8S2. What is the oxidation number here? Plus 2. Oxidation number plus 2 means D8 is remaining. Now how to check it? Whether it is weak field or strong field. Yes, in D8 electronic configuration, just now I shown to you, either in strong field or weak field, the distribution of electrons is same. Either it may be strong field or weak field. Yes, amine is strong field. If it is weak field also, distribution of electrons is same. Therefore, the third option is correct. T2G6 EZ2. Questions are appearing in this way on this particular table. It is very important, but easy concept also. See, under crystal field theory, one by one we are continuously discussing. First I discussed postulates. Next, splitting of d orbitals and factors influencing splitting of d orbitals. I introduced to you what is spectrochemical series, what is its importance, and I shown how the electrons are distributed in T2 and EZ orbitals. Then let us come to the application part of the crystal field theory. Applications of crystal field theory. Applications. Suppose in the examination a complex is given in like this, FeF6 minus 3, for example I am giving this. They may give a question on this particular, they will put a question to it, number of, what is the hybridization of this, how many unpaired electrons are there, what is the magnetic moment, what is splitting of d orbitals and how the electrons are distributed. Any question may appear on this particular ligand. So that first you take iron, yes, Z equal to 26. In this way we have to solve this particular complex step by step. Try to understand, observe the board. Then its configuration is what? 3d6 4s2. Let's check the what is the oxidation number. 6 minus charges, 6 minus ligands are there, minus 3 remaining. Oxidation number is what? Plus 3. Here in plus 3, the remaining configuration is 3d5 4s0. 3 electrons lost, 3d5 4s0. Next, the electrons in this particular 3d orbitals in the free metal ion 1, 2, 3, 4, 5. next s orbital. This is. Now take the complex Fe F6 minus 3. Fe F6 minus 3. Already given the nature of the fluoride ligand, it is weak field ligand. What is the meaning of weak field? Weak field means it is not pushing the electrons to pair up. That is the actual meaning of this. Now let me write here F weak field. I am writing like this, F weak field. No pairing of electron takes place. D orbital electrons remaining as D orbital, electrons remain as D phi. Yes, 1, 2, 3, 4, 5. After this, 4s and again 4p. 4s and 4p. And let me write one more also, 4d. 4d. So coordinate number is what? 6. You require 6 orbitals. Look here, 1, 2, 3, 4, 5, 6. The type of hybridization, this is what? S P3 D2. The type of hybridization Sp3 D2. So you can understand now in Fe F6 minus 3, the hybridization taking place is Sp3 D2. This particular diagram we can call it as valence bond diagram, valence bond diagram. Valence bond diagram, or you take you can also call it as what? Box diagram. Valence bond diagram or box diagram you can see. Next I will show fitting of d orbitals in this particular complex, how the electrons are getting distributed, how the d orbitals are splitting. Splitting diagram you see. D orbitals, 5 electrons. After the splitting, this is the distribution of electrons. You know this particular is the set of orbitals. This is T2 the set of orbitals. Say this is what? Delta O distribution 1, 2, 3, 4, 5. This is a distribution of electrons. So this is a diagram, distribution of electrons, and this is what? Hybridization. For each complex, we should be in a position to write the information about the complex. What we have discussed, what we have solved, what we have cleared about this particular complex, we put in the form of information. What information we are getting from this particular complex or this particular complex. Come on, say first hybridization. Yes. Consider geometry. Hybridization, geometry, nature of the complex. Nature of the complex means whether it is inner orbital complex or outer orbital complex. What is the nature of the complex? Number of unpaired electrons. Number of unpaired electrons. Number of unpaired electrons. And you can consider magnetic moment. Magnetic moment. So hybridization, geometry, nature of the complex, and again number of unpaired electrons and magnetic moment. See hybridization, we thoroughly discussed sp3d2. Geometry coming to be octahedral, and number of unpaired electrons 5 you are looking on the board, 5. Nature of the complex. Now first one, this is what? Nature of the complex. First let me write nature of the complex, then we go for this number of unpaired electrons. Nature of the complex, it is what? Outer orbital complex. This we can also say it is what? High spin complex, or say spin free. Outer orbital complex, high spin complex, and spin free complex. Number of unpaired electrons you are looking on the board 5. See 5 unpaired electrons. Once 5 unpaired electrons are there, the magnetic moment coming to be 5.9 bm. 5.9 bm. So this is the information: hybridization, geometry, nature of the complex, outer orbital complex, high spin and spin free. Number of unpaired electrons 5, magnetic moment 5.9. This way we can write the information about this particular complex. Let me give few more complexes how we can discuss this particular, how we can write the information of this particular complex. One more complex I will give, similar way we will discuss, like that 5-6 examples I will give and discuss all these. So one more complex I am giving, say second one, FE CN taken 6. Consider this is the complex. Same steps we put what we have just taken in the previous case. Now iron, that is equal to 26. The configuration was 3d6 4s2. 3d6 4s2. Next, what is the oxidation number again? Oxidation number coming to be plus 3. This is 3d5 and 4s0. Then the d5 electronic distribution I am writing like this. 5 electrons are there. 1, 2, 3, 4, 5. This is what 4s0. In the free metal ion, the electrons are actually arranged like this. Then after the complexation, right, I am writing a complex Fe Cn taken 6 minus 3. Cn is what a strong field. Cn is strong field ligand. Say what happens by strong field ligand? What I said, a weak field ligand is the not capable of pushing the electrons to pair up. Whenever you are taking a strong field ligand, it pushes the electrons to pair up. Then since it is a strong field ligand, the 5 electrons are getting paired in the d orbitals. Now you see the 5 electrons getting paired 3d 1, 2, 3, 4, 5 electrons. Next you take this is 4s. You can consider next one 4p, 4s and 4p. Then coordinate number is 6. 6 orbitals are required. Look here 1, 2, 3, 4, 5, 6. This will be the hybridization D2sp3. But I said this is known as what? Valence bond diagram or box diagram. This short form I am writing valence bond diagram or box diagram. Valence bond diagram or box diagram. For this again you have to show the splitting of orbital. See, splitting of orbitals, d orbitals, 5 electrons. After the splitting, this is the splitting of orbitals, Eg, T2G, delta O. So since this particular cyanide ligand is strong field, electrons are getting paired in the lower energy level. Then here in the lower energy level, see 1, 2, 3, 4, 5. Look here. The previous case, the 5 unpaired electrons are remaining as such, since that is actually weak field. But here it is actually strong field. The 5 electrons are getting paired. You are clearly observing that 2 pairs and 1 unpaired electron. Let us write the information about the complex information. Come on now, hybridization, geometry, nature of the complex I said, number of unpaired electrons I said, number of unpaired electrons, and magnetic moment. Check it, hybridization, yes, you have solved it, D2sp3. Coordinate number 6, then you can say it is octal geometry. The number of unpaired electrons, you are looking only 1. Nature of the complex, no? Yes, here nature of the complex. Then you say it is inner orbital complex. Inner orbital complex, you say low spin or spin paired. Inner orbital complex, low spin or spin paired. Number of unpaired electrons, only 1. Magnetic moment 1.7 bm. Magnetic moment 1.7 bm. So first one we have discussed FeF6. Second one we have discussed this one FeCN taken. What is the difference between these two? Fluoride ligand is weak field ligand, cyanide ligand is strong field ligand. That is only the difference we are finding between the first complex and the second complex. Now let me show 1 or 2 cobalt complexes. Next one, you see CO, F6 I will give. COF6 minus 3. COF6 minus 3. Come on, same steps we put. Now CO that is equal to 27. This is 3D7 and 4S2. Oxidation number coming to be again plus 3. Yes, it is 3D6 and 4S0. 3D6, 4S0. The distribution of electrons in d orbitals, this one. 1, 2, 3, 4, 5, 6. This is 4S. Let me write the complex similar way. For all the complex I am putting the same number of steps and similar way I am explaining so that you can easily follow. F is weak field. Weak field. The weak field case, the electrons are not getting paid, remaining same. Look here, this is our 3D, 4S, 4P and 4D also I am writing here 4D. 3D, 4S, 4P and 4D. The no electrons getting paired because it is getting paid because it is weak field, the remaining same. 6 ligands 1, 2, 3, 4, 5, 6. Then it will be sp3d2. sp3d2, this we can consider as what valence bond diagram or box diagram. Valence bond diagram, box diagram. Coming to the splitting of d orbitals, already diagram is there. How many electrons are there here? 6. Yes, 6 electrons. It is what weak field, the distribution of electrons 1, 2, 3, 4th electron, 5th electron and 6th electron. This is the way the electrons are actually arranged after splitting. 1, 2, 3, 4, 5, 6 electrons. Come to the information part. Now, information you see in the case of this particular complex, what we have discussed. Hybridization, I clearly shown on the board. This is what sp3d2. Geometry you can say, coordinates number is 6. Geometry coming to be octahedral. Nature of the complex. Either 4D orbitals are involved, say outer orbital complex or high spin complex or spin free complex. Spin free complex, no pairing of electron. Outer orbital, high spin and spin free complex. Number of unbundled electrons, how many number of unbundled electrons? 4. Magnetic moment, you can take 4.87 bm. 4.87 bm is the magnetic moment. One more complex I will show, the last one. So now I will take next, here it is what F is what weak field. I will take one strong field ligand and I will show how this particular distribution of electrons and all we will discuss. See, this particular complex, instead of writing now weak field, I write a complex with a strong field ligand. Take CO, NS3 taken 6 and plus 3. Same steps, cobalt 3D7 4S2 and cobalt is again plus 3 oxidation number, same. But only the difference you find is fluoride ligand is weak field, it is strong field. Just here I will remove and put the diagram again, rewrite. I rewrite the diagram again. This is the first step, second step. Consider the complex CO, NS3 taken 6, NS3 taken 6 and it is plus 3. This is what NS3 is what strong field. NS3 strong field. Yes, you know what I said, strong field means electrons are getting paid. This particular 6 ligands, 6 electrons, 1, 2, 3, 4, 5, 6. 6 electrons getting paid because NS is what a strong field. Then 4s and 4p. 4s and 4p. Coordinate number 6. 6 orbitals required. 1, 2. This you say as 3D. 1, 2, 3, 4, 5, 6. This one will be D2, sp3. It is valence bond diagram. you see box diagram, valence bond diagram or box diagram. Next, splitting of d orbitals. How many electrons? This particular again 6 electrons. Here 6 electrons. Here the 6 electrons because of strong field. These are getting paid. 1, 2, 3, 4, 5, 6. 6 electrons are getting paid there. Next, but the information about the complex. Information about the complex. Look here. Hybridization D2sp3. Geometry of the complex octahedral. Nature of the complex inner orbital 3D is involved. So, inner orbital complex, low spin complex, spin paid complex. Inner orbital complex, low spin complex, spin paid complex. Number of unpaired electrons you are looking here. No unpaired electron, 0. Magnetic moment also 0. This is the way when a weak field ligand is there, the strong field ligand is there, how this particular cobalt complexes are involved in different hybridizations and carrying different number of unpaired electrons and magnetic moment. So, what you have to observe is whether the ligand given is weak field ligand or strong field ligand. Accordingly, whether to pair up the electrons, not to pair up the electrons, you have to understand and observe. Then accordingly, you have to write all these steps, splitting of orbitals, information about the complex. Students, today we are going to discuss splitting of d orbitals in square planar geometry. Splitting of d orbitals in square planar geometry. To understand the splitting of d orbitals in square planar geometry, we should be thorough with the splitting of d orbitals in octahedral geometry. Octahedral geometry only modifying to get the crystal field geometry or crystal field splitting. So, you see now, if you are considering octahedral geometry, imagine this is what a square plane, and from top and bottom you see this is what axial. The square planar geometry, two ligands are there in the axial position, then that will be a octahedral geometry. Now, if you are removing the two ligands from octahedral geometry in the axial position, the remaining geometry is what a square planar. By the removal of two electrons, two ligands from axial position, then what is happening, what modification is taking place, what change is taking place in the octahedral geometry, we have to discuss it. For that, we have to put first a octahedral splitting diagram. The octahedral splitting diagram, how it is changing to square planar geometry, that we have to discuss. For that, we have to put both the diagrams. First, octahedral splitting, how it is changing to this square planar, we have to discuss with the help of this particular diagram. See, I am putting the diagrams first octahedral, and I am showing that how this octahedral geometry changing to give rise to a square planar splitting diagram. See what I am writing first, it is what this octahedral splitting I am showing on the board. This you know dxy, dxz, dyz, d square minus y square and dz square, 5 d orbitals in octahedral. Then these are actually 5 degenerate d orbitals. These are splitting like this, octahedral splitting. Take it as easy, it has what t to the. Let me write this is what 5 degenerate d orbitals. Degenerate d orbital. 5 degenerate d orbitals in octahedral geometry splitting into two energy levels T2Z and EZ. Now you can see this particular diagram in octahedral geometry. Now I am writing here this particular T2Z set of orbital dxy, dxz, dyz. This is dx square minus y square and dz square. This is splitting of d orbitals in octahedral. This now we have to discuss. This is octahedral geometry. What I said, from the octal geometry, the two axial ligands you are removing, the generated geometry is what? Scale planar. Now, this is, let me write octahedral. I am putting a small octahedral diagram here. So, look here, this is what octahedral. This is octahedral splitting. Now, once you are removing the two ligands from octal geometry, from the axial position, that means the dz square orbital not exhibiting any repulsion. Dz square orbital is not exhibiting any repulsion. Its energy is what? Decreased. So, I am bringing this particular dz square orbital below the center of gravity. Below the center of gravity, look the board. This is right, I am writing here just below the center of gravity. Let me take it as what? Dz square. Next, once the means one of the direction and the one of the axis, if you are removing the ligands, the other axis means what? Along x axis, along y axis, the ligands are coming very near to the metal ion, Therefore, the ligands along x axis and y axis coming very near to the metal ion. The orbital which is oriented along x and y, this is x axis, imagine y axis. The ligands which are there on x and y axis coming very near to the metal ion. By this, the dx square minus y square orbital experiencing greater repulsion. Therefore, its energy is what? Increased. Therefore, in the scale planar geometry, the highest energy level is what? This dx square minus y square orbital. This is dx square minus y square orbital. Highest energy level in the scale planar geometry is what? Dx square minus y square. What I said, once you are removing the ligands along z axis, the repulsion along the z axis, that means the dz square orbital not experiencing any repulsion, its energy decrease. Once you are decreasing or removing the repulsion along one axis, in the remaining axis the ligands are coming very near. Therefore, the ligands along x axis and y axis coming very near to the metal ion. Therefore, the orbital which is oriented along x and y axis, that is dx square minus y square orbital experiencing greater repulsion, its energy is increased to very high value. So, highest energy level in this particular scale planar geometry is what? Dx square minus y square orbital. Next, see this particular dxy, you know the dxy orbital is oriented in between the axis. No, you see now this particular consider is what? X axis, this is y axis. This particular orbital is actually oriented. Which orbital I am saying? dxy is oriented in between x and y axis. Now, we know this particular ligands are coming along x axis and also y axis. Then, in between this particular two axes, what to say? That is dxy. Once the ligands are approaching along x axis and y axis, the orbital which is oriented in between this axis, this is what? dxy, as is shown on the board. This particular dxy is experiencing some repulsion, not the direct repulsion, some partial repulsion on the dxy. Therefore, dxy is increasing its energy. So, there will be increase in the energy of a dxy orbital. Dxy is just increasing its energy. Then, I am writing little above the center of the gravity. This is dxy. Now, along the z axis there is no ligands, we said in the case of scale planar. Along the z axis there is no ligands along z axis. Therefore, now the dxz and yz are not experiencing any repulsion. What you can consider, the dxz means this is z axis you take, right? This is z axis. Then this is what? Dxz orbital. This is what? Dyz orbital. This is dxz you consider. This is yz. The dxz and dyz orbitals not experiencing any repulsion. Their energy is what? Still decreased. Their energy is what? Decreased. This will be the dxz dyz. The lowest energy level in the scale plane or geometry is what? Dxz. Now, the total energy difference between the lower energy level dxz to higher energy level dx square minus y square we can represent by delta Sp. Delta stands for energy difference say, and Sp stands for square planar geometry. This is represented by what? Square planar, the splitting energy, the d orbital splitting energy for square planar geometry. The total energy difference between dxz yz to higher energy level x square minus y square represented by delta Sp. It is known as what? D orbital splitting energy for square planar geometry. This is the order of energies of orbitals. Now, dxz yz is lowest, less than dz square, less than dxy, and less than x square minus y square. Highest energy level, lowest energy level. This you have to remember order of these particular orbitals. Next, look here. This particular square planar splitting I have shown on the board. This you are clearly observing. This is more than octahedral splitting. This is more than octahedral splitting. Why? In the case of scale planar geometry, the splitting is more than this particular octahedral. Actually, the scale planar geometry, the geometry is only carrying 4 ligands. And octahedral geometry, it is carrying what? 6 ligands. It should be, what should be? Scale planar splitting should be less than octahedral. But we written on the board, scale planar is more than octahedral. How to explain this particular fact? Now, this particular 4 ligands in the scale planar geometry, I am writing here scale planar C. This is scale planar, square planar. Now, so in the square planar geometry, all the 4 ligands are experiencing, all the 4 ligands are showing maximum repulsion on the orbital which is oriented along x and y axis. The 4 ligands are showing complete repulsion on only dx square minus y square orbital. By this, the dx square minus y square orbital is increasing its energy to very high value. By this, the energy difference between lower energy level dxz yz to higher level dx square minus y square is becoming more. Therefore, delta Sp is more than delta O. Delta Sp is more than delta O. Then it will be delta Sp is equal to 1.3 times of delta O. 1.3 times of delta O. So, delta Sp is more than delta O. For this, what explanation we are giving? All the 4 ligands are showing complete repulsion on only dx square minus y square orbital. Therefore, its energy is increased to very high. Once one of the orbital is increasing its energy to very high value, the lower to higher energy energy difference is becoming much. Therefore, delta Sp is more than delta O. So, delta Sp equal to 1.3 times of delta O. This relation is very important to remember. This is the splitting of d orbitals in square planar geometry. Next, we see the splitting of d orbitals in tetrahedral geometry. Now, let us discuss the splitting of d orbitals in tetrahedral geometry. We have discussed in the splitting of d orbitals in octahedral geometry. Next, square planar geometry. Now, we discuss how the d orbitals getting split into tetrahedral geometry. To understand this particular splitting of d orbitals tetrahedral geometry, let us consider a cube. Let us put a complex in the cube and see how they are oriented. According to that, we can easily understand the splitting of d orbitals in tetrahedral geometry. Now, I am writing a cube on the board. See, a cube putting on the board, and let me say metal. This is actually linked to 4 ligands. These are the 4 ligands and one more ligand like this. See, as I shown on the board in tetrahedral geometry, a cube we have taken, a tetrahedral complex with 4 ligands. I put into this particular cube. Look here. Then let me call this particular x axis. Let us consider this is what z you take. This is z axis, and one more. This one is y axis. So, x y z. 3 axes, and the metal ion, let me write to represent this particular metal ion plus or minus oxidation number. You are clearly observing on the board the 4 ligands of the tetrahedral geometry, the 4 ligands of tetrahedral geometry occupying 4 corners of the cube. First point, 4 ligands of the tetrahedral geometry occupying 4 corners of the cube. Second point, you clearly observe on the board, these 4 ligands are actually occupying or oriented. These 4 ligands are oriented in between the axis. See, in between this axis, in between this, in between this, in between this, the 4 ligands are actually oriented in between the axis. By this, what you can understand, this particular sp3 hybrid orbitals also oriented in between the axis. sp3 hybrid orbitals also oriented in between the axis. We can understand like this. This is what sp3 hybrid orbitals oriented in between the axis. Just to try to follow this particular. Next, I am putting the diagram now. How this particular d orbitals are getting split now. 5 d orbitals, dxy, dxz, dyz, dx square minus y square and dz square. This is what you say 5 degenerate d orbitals. D orbital. Next, see, these are splitting into higher level in this particular tetrahedral is what? This is T2 is the set of orbitals. This is T2. In tetrahedral geometry, instead of writing T2G and EG, we represent only by E and T2. E and T2. Now, this is d square minus y square. This is dz square. D square minus y square, dz square. E set of orbital, or say EG set of orbital, but tetrahedral geometry we represent only by E and T2. dxy, dxz, dyz. Let us consider center of gravity. This, let me say delta. Since you are talking about tetrahedral geometry, I am writing as what tetrahedral T. Delta stands for energy difference between the lower energy level and higher energy level, and T stands for tetrahedral geometry, delta T. Here the energy of this particular T2 set of orbitals, it is actually plus 0.4 delta T or plus 4 dq take. In the case of each set of orbitals, minus 0.6 delta T, minus 0.6 delta T, or you can consider minus 6 dq, minus 6 dq. This is delta T, or you can also say this value as 10 dq, 10 dq or delta T. Now, come to our point. See, in the case of tetrahedral geometry, the lower energy level is what? EG or E set of orbitals, higher energy level T2 set of orbital. The increase in energy of this particular T2 set of orbitals is plus 0.4 delta T or 4 dq. In the case of EG set or E set of orbitals, this is what? Plus 0.6 delta T or minus 0.6, sorry, minus 0.6 delta T or minus 6 dq. This is the energy difference. Now, the total energy difference between lower energy level and higher energy level is represented by delta T or 10 dq. Now, how this particular splitting is taking place and what are these energy differences, we will discuss it. Just now I said, in tetrahedral geometry, the 4 ligands are occupying 4 corners of the cube, and these 4 ligands are actually oriented in between the axis. Clearly you are observing in between the axis. No ligand exactly falling on the axis, all are oriented in between the axis. Next, by this what we can understand, the sp3 hybrid orbitals also oriented in between the axis. sp3 hybrid orbitals oriented in between the axis. Now once a ligand is actually forming a bond with this particular sp3, the ligand has to approach toward the metal ion. The ligand has to approach toward the metal ion through the way in between the axis. This ligand has to approach toward the metal ion to form a bond with sp3 in between the axis. In between the axis, you know, in between the axis, the orbitals oriented are what again? T2 the set of orbitals are oriented in between the axis. T to the set of orbitals are oriented in between the axis. Imagine this like this, you can say this is what T to this EG set of orbitals, this is T to the set of orbital, this is sp3. Once a ligand is actually forming a bond with this particular T2 set of orbital, this T to the this particular once a ligand is forming a bond with sp3 hybrid orbitals, these T2 orbitals are coming near. Therefore, T2 orbitals are experiencing little more repulsion, therefore their energy is what increased. Therefore, the T2 orbitals are increasing their energy, increase will be plus 0.4 delta T or 4 dq. Next, look here, each set of orbitals actually oriented along the axis, they are away from the ligand. Ligand is here, EG orbital here, ligand is here, EG orbital here. So, you can understand this what I said, you see, this is T to the set of orbitals, this is EG set, this is EG set of orbitals, this is T to the set of orbitals, this is sp3. Once a ligand is forming bonding with the sp3, the T2 is coming very near, EG is what little away. Therefore, EG is actually decreasing its energy and T2 is what increasing its energy. That is the concept here. So, in tetrahedral geometry, the energy is increased for T2G set of orbitals, increase will be plus 0.4 delta T or plus 4 dq. In the case of this particular EG set of orbital, decreasing their energy, there will be minus 0.6 delta T or minus 6 dq. Now, the total energy difference between lower energy level EG set of orbitals, higher energy level T2 set of orbitals represented by delta T or 10 dq. It is known as what? D orbital splitting energy for tetrahedral geometry. Next, tetrahedral geometry is not a perfect symmetric geometry. Therefore, instead of T2G we are writing T2, instead of writing EG we are writing E. G stands for gerade or it is symmetric, gerade or symmetric. Therefore, since this particular geometry is not a perfect symmetric geometry, therefore, for splitting of d orbital in tetrahedral geometry, we are only representing by T2 or E. So, these are the splitting of d orbitals. First, I discussed in octahedral geometry, scale planar geometry and tetrahedral geometry. Next, you are clearly observing in the case of tetrahedral geometry, the splitting of d orbitals is completely reverse. No. So, in the case of octahedral, each set of orbitals we written as what a higher energy level, but here we are written as what a lower energy level. So, in comparison to octahedral geometry, the splitting of d orbitals in tetrahedral geometry completely reverse or opposite to the splitting of octahedral geometry. Next, look here, delta T is less than delta O. You can easily understand. In the case of delta T, it is only repulsive interaction due to 4 ligands, right? In the case of octahedral geometry, it is due to what? 6 ligands. In tetrahedral, it is due to 4 ligands. In octahedral, it is due to 6 ligands. Therefore, repulsive interactions are less in tetrahedral, repulsive interactions are more in octahedral. Therefore, splitting of d orbitals in tetrahedral geometry is less than octahedral splitting. This is what you can say, delta T is less than delta O. Yes. Now, delta T is equal to 0.45 of delta O. Yes. You can also represent delta T. Delta T is equal to 4 by 9 of delta O. Either the way you can represent the relationship between tetrahedral splitting and octahedral splitting. So, overall 3 splittings, one is octahedral, square planar and tetrahedral. These are the splitting of d orbitals in 3 geometries.